All right, everybody. Welcome to VSA Online. It's 8 p.m. GMT, and I'm very happy to see you all here online. And it's my special pleasure to welcome Dr. Madison Cotteret, newly baked doctor. So, without any further delay, Madison, the floor is yours, please.
Hello. Right. Um, can I get rid of myself? Yeah. No. Shit. Cool. Can you everyone see my screen? Is that good?
Yes.
Very good. Okay. Um, Lovely. So before I get on to talking about making continuous attractor networks using sparse block codes and more generally the VSA framework, I want to give a very brief overview of why I'm looking at attractor networks at all, and also why I'm looking at VSAs and trying to combine them with attractor networks. So I'm coming at this from the field of neuromorphic computing, which, to give you a bird's eye view of the field, the idea is that we want to take our understanding of biological neuron and synapse dynamics and then to build silicon neuron and synapse circuits which emulate these dynamics with a goal trying to achieve computation much more efficiently in this kind of hand wavy bio-inspired way. So here we have a neuron chip which we built recently, which consists of neuron circuits not like this one, and these neuron circuits have time varying and spiking, much like their biological counterparts, and they're all operating entirely asynchronously. So it's not as if we have a system that's working with clocks or that's working with frames, for example. And now that's the good parts that we're inheriting from biology. But unfortunately, and especially in analog neuromorphic hardware, we inherit a lot of the, I guess we would say, difficulties. So much like in biology, how there's always going to be some unavoidable degree of synaptic noise, whether that be from biochemical processes or from again, unwanted spike activity outside of your network, for example. In analog neuromorphic hardware, you always have some degree of thermal noise or crosstalk, which is making your neurons behave stochastically or have undesired behavior. Similarly, whilst in biology, you will always have some degree of heterogeneity between different neurons and synapses, or rather between the same classes of neurons, say. In neuromorphic hardware, a neuron with the exact same design, but shifted by a few micrometers, might have very different characteristics to his neighbor, simply due to the mismatch between their two circuits, which is somewhat unavoidable. So the question then arises, well, how can we, despite all of these non-idealities, still begin to build up systems which function robustly despite being built out of fundamentally unreliable components? Now, the solution posited to us from biology is that we should turn towards attractor networks. And so I'm going to talk about discrete attractor networks first, but this should flow quite naturally into continuous attractors. So if we here look at possibly the simplest attractor network, which I guess most of you are already well aware of, we have a hot field network consisting of an all-to-all connecting network of binary neurons. So Z1 through to Zn, where n is very large. Let's say it's 1,000 or 10,000 neurons. And these neurons have a sign activation function. So on every time step, the neurons project back to themselves via their weights matrix. And then if the postsynaptic sum is greater than or equal to 0, then the neurons will then that neuron will go to a +1 state. Otherwise, it will go to a -1 state. Then what we know is that if we construct our weight matrix to be out of a Hebbian outer product learning rule like such, so each of these x's is an independently generated bipolar hypervector. Well, Mr. Hopfield didn't call it a hypervector, but it may as well be a hypervector to us. Then the dynamics of your network can be vastly simplified to simply a descent on some energy function. And quite conveniently, our energy function consists of parabolic energy wells at each of our at each of our hypervectors or vectors that we use to create the weight matrix. So what this means is that if we have a network where we've initialized it near one of the bottom of these energy wells, then as the network iterates, your network state will effectively roll or converge to the bottom of your energy well and then sit there very stably for a long time. Now, this is very, very, very good for neuromorphic computing because it says, okay, we can now build very robust state holding elements using large networks of unreliable components. Great. But this doesn't yet tell us how we can begin to use these sort of networks in order to build up more capable computational functions, shall we say. And for that, what I want to do is bring in the machinery and the structure of VSAs in order to make attractor networks do more, basically. So in a previous VSAONLINE session, I already spoke at excessive length about how to embed discrete computational structures into Hopfield networks. So in this case, we're looking at a finite state machine. So we have a very simple one here, 3 states, 1, 2, and 3. And we create hypervector representations of, we create a hypervector representation of this state machine by, for example, generating hypervectors to represent state 1, state 2, state 3, but also hypervectors to represent the stimuli and each of the edges and transitions, such that we can then build an attractor network which emulates our choice of state machine. So not only do we have our state holding dynamics now, such that well, you start your network off in state 1, it sits there. But if you give the input A, which is some hypervector, you will jump between the correct energy wells. And this, of course, has an equivalent literal neural description. And new to what I presented last time, because this network is so robust, because it's using Hopfield network as a backbone, basically, you can take this network and then just in one shot or zero shot maybe, simply deploy it onto neuromorphic hardware and it will just work. Which, if you believe it, but if you'll trust me, is a property which you normally cannot expect of neuromorphic hardware due to the aforementioned difficulties of mismatch and noise, etc. So here we have, so I'll quickly show an example of that. So here's a state machine with 23 states for doing a modular division of numbers by 23. So for each of these states, 0, 1, 2, 3, ... we generate a sparse block vector. So here we have an example here, and we store that sparse block vector into a Hopfield-esque associative memory to represent it. Now, for those that aren't already aware, a sparse block vector is just a vector whereby we've split our end neurons up into blocks here of size L equals 4, and then the random aspect of this is then that exactly only one neuron in each block is active, which is randomly selected. Now, my focus on sparse block vectors coming from neuromorphic computing is due to the fact that it's very easy to map sparse block vectors to spiking networks, because in order for your spiking neurons to emulate this, in order for your spiking neurons to represent this sparse block vector, you simply need to wire your neurons together such that, let's say you have 4 neurons representing one neuron representing each index of this block. Then as long as your neurons are wired together such that only one neuron in that block can be active or can spike at any time, then your network will be confined to representing sparse block codes, which makes your life a lot easier. Also, the fact that in other work, which I haven't cited at the bottom here, sparse block codes are very useful for making they in some ways maximize the capacity of your attractor networks, which we are assuming here. Which is very useful. So if we look here at the spikes in a network that's been constructed in this way, we can look at any time and see that the network is indeed representing a sparse block vector, but here with blocks of length L equals 8. So you can see here, only one neuron is active, only one neuron is active, one neuron is active. I have no idea what's going on here. That looks glitchy. And if you just trust me, it's doing the correct walk between attractor states, or it's doing the correct walk between sparse block vectors representing attractor states. Yep. So that's good. And it's telling us how we can generate, how we can embed discrete computational primitives like the state machine into attractor networks. But what we're really interested now is how we can generalize this to continuous attractor networks. So, hello.
Just real quick, like what exactly is driving it between like temporarily, like why is it transitioning or?
Yes, I'm gonna have to go to the end. I'm gonna have to go to the end to show you that. That'll be spoilers. So the inputs that we're giving to the network are inhibiting certain blocks. So you can see here
Okay, you're driving it to transition with
yes.
like, okay, yeah, just okay.
Yeah, so that's quite important. So between this time here, you can see half of the blocks suddenly disappear. That's because they're receiving inhibitory input, which kind of activates some VSA terms within your weights matrix, and then yeah, so then essentially you're driving it to make certain transitions, which we are also going to do for the continuous attractor networks. So
Right.
okay. So continuous attractor networks were first conceived to answer questions like how can a rat keep a memory of, well, how can a rat keep track of which direction it's facing, even if it's completely in the dark, for example? And the answer, perhaps not surprisingly, was that in order to keep track of the direction it's facing, then it must somehow be keeping a memory of the direction it's facing, I guess. And so that requires that somewhere it has a neural representation of the continuous variable from 0 to 2 pi representing the angle that it's facing. Now, more recently, good news, measurements from the rat brain have confirmed this and found there is a literal ring of neural activity states which do represent the direction the rat's facing. That's quite remarkable. But I'm going to concentrate a bit more. I'm going to concentrate more on the models that were used or initially proposed to realize these kind of dynamics. And those are bumper tractor models. So given the fact that you want to represent neurons in a ring, it seems quite reasonable. Well, the initial models then arranged neurons in a ring and then gave them the stereotypical nearby excite far inhibit connectivity such that localized bumps of activity were then stable on the ring. And these are the ring attractor networks or bumper tractor networks, which you've probably heard a reasonable amount of. And then there's also some extra machinery such that the bump can move around the ring in response to input. Now, I'll elaborate on it a bit more later, but these networks have quite a bit of a critical flaw in that they are really heavily reliant on having perfect synaptic connectivity, such that no position on the ring is favored over any other one. You have a perfect symmetry in your synaptic weights as you translate around the ring. And if you disturb this symmetry at all, then your continuous attractor dynamics break down. But we'll see a bit more on that in a second. So the question then is, can we use our previous approach of that we were using to put finite state machines into Hopfield networks to now instead put continuous attractor networks into Hopfield networks? And for that, we need a method of generating sparse block code vectors, which don't represent discrete symbols now. Which don't represent discrete symbols now, but instead can represent continuous quantities. So very heavily inspired by random Fourier features, if you're aware of those, aware of that. This was the simplest thing I could come up with. And when looking at this function, you can also just look at the figure on the right to see what the output of it is. So this function is determining for any p, So P is our one-dimensional position that we're trying to embed. Our one-dimensional position for which we're generating sparse block code vectors to represent it. We're multiplying our P by some omega, and then this represents a kind of pseudo phase, I would say, because it's bound to the range 0 to L, and then we're picking a random threshold on the domain of 0 to L, on which the neuron will be active. Otherwise it'll be inactive. So I guess you can see this. Hello.
Yeah, Madison. But you didn't come up with this. Is this the Raginsky in Lazebnik model, or is there some difference? Or I mean, it's very similar to it, right?
So initially, I just took the random Fourier features from Rahimi and Recht and said, well, what would a binary version of this look like? But then the Raginsky and Lazebnik, they have a similar version of this, but it is slightly different. But
in essence, I mean, it's very similar, right?
It's very similar, but it doesn't have a fixed sparsity, which is the difference here. But yeah, if you want other versions of random Fourier features but have been converted to binary codes, then Raginsky and Lazebnik are your guys or gals. Okay, where are we? Okay, so important to note is that these omegas and thetas are set such that the sparse block code representation is they are set such that the vector representing P has exactly one neuron active in each block for any P. So we just have a very convenient way to go from a low-dimensional P to a sparse block code representation. Now, in each block, these omegas are sampled from some probability distribution P of omega. So this is, I guess, the same P of omega that we'd have in random Fourier features, and also other variants. And the important property that this embedding has is that you have a nice translation invariant kernel. So if we define a scaled kernel here, the inner product between two sparse block flows representing a position is just given by the difference between the positions they represent. So here we have the P of omega, which is determining which is the distribution from which these omegas were drawn. And so we have the samples and then the ideal distribution. And then on the right in black, we have the ideal theoretical kernel that we should have. And then just behind that, we have a few instances of the actual realized inner product between two vectors as you're varying the P of one of them. And for those who are interested, you can link this quite nicely to the kernels and random Fourier features, since you can write the kernels as this, where P hat is the Fourier transform of your probability distribution P, and so this is the kernel from random Fourier features. Okay, so we now have a way of representing 1D positions using sparse block code vectors. Now we should simply try and make a line attractor using these vectors. So while in the Hopfield network, we constructed the weights simply as a sum over the discrete states that we wanted to add in our network. Since we now have a continuum-ish of states that we want to store in the network, we can simply generalize this to an integral rather than a sum. So we're going to integrate over the positions piece over the line that we want to embed as an attractor. And since we know that the states we want our network to represent are sparse block codes, we'll equip our neurons with what I call a block winner take all activation function. So within every block of neurons, we will have we imagine there is some winner take all connectivity such that only the neuron with the greatest input is allowed to spike. So you see here, if we have a weirdly small block length of L equals 2. If one neuron is receiving 3 and his competitor is receiving 4, then only the neuron receiving 4 becomes active. So this is a sparse block code with L equals 2 again. Okay, so we can construct a network in this way, give it this update rule, and let it rip. So here we're starting off our network at multiple positions separately, and then just seeing how it evolves. And ideally, what we'd be seeing here, if this was a perfect continuous attractor network, is simply a set of perfectly straight vertical lines, implying that we start our network off at some position, and over time it stays in that position perfectly. That would be your ideal conception of a continuous attractor network. However, what we actually see is that your network state is attracted to a few preferred points along your line attractor. And so what we really have is a few discrete attractor states to which your to which your network is attracted, and therefore your network can only really store a very low resolution representation of the position that you're trying to encode. And down here we have the energy function, which we can calculate for the network, and you can see approximately that your network state is indeed avoiding the peaks of your energy, and it's going to the troughs here, for example. So that's not good. But if we look back in the literature, we see even in the earliest models of bump attractors, so from Zhang in 1996, they also indeed encountered this problem, that the moment you introduce even a small degree of synaptic heterogeneity to your network, you no longer have your idealized continuum of states, but actually you end up with, I don't know, 1, 2, 3, 4, 5, 6-ish stable states to which your network is attracted, and therefore you're actually only storing, you're not representing your continuous variable very well. You're in fact representing it with a very low resolution. Hello?
Madison, I have another question.
Hello, please.
So is it okay? So yeah, the energy landscape is bumpy, I guess, right? And so, but it's like random codes, and so is it randomness? And like, does it get less bumpy with bigger vectors? And or is it not that alone? Is it something because the kernel isn't certain shape or not? Maybe there's some other reason why it's bumpy. Do you know?
Yeah, that's good question. So yeah, the kernel bumpiness is due to the fact that your inner products aren't exactly your kernel, but actually have a certain degree of noise associated with them. And if you make some horrible approximations about what that noise looks like, you can then work out what the statistics of the bumpiness of your energy landscape are. I've forgotten how the bumpiness of the energy landscape relates to n, but I would assume probably yes, if you're in an infinite n regime, maybe your energy landscape flattens again. So the bumpiness of the energy landscape is very much dependent on the fact that your inner products aren't exactly your kernel, but are actually, if we go back, I wonder if I can zoom in, but are actually a bit of a bumpy mess around your kernel. Did that answer your question?
I mean, I guess it's really important to discern here two different types of noise, right? In your in your line attractor world, right? One is really this noise with which the kernel is approximated, and this serves like little local minima in an energy function, in a constant energy function. But then the diffusion that you would even get if you would have perfect kernel approximation, and even get stronger because your state wouldn't get stuck in these local minima. That's additional noise that you impose here in the simulations, right? And that's of course the same what Zhang was doing, and why you get these trajectories in Zhang.
Yes. So as Fritz pointed out, as well as I somewhat failed to mention that I'm also blasting these systems with quite a high degree of fast stochastic noise to emulate that well, they're constantly being bombarded with noise, and therefore, even if you had a perfectly flat energy landscape, you would actually start drifting about it just due to being bombarded with random noise. But due to the fact that your landscape is very bumpy, and actually we're dealing with discrete attractor dynamics here rather than continuous attractors, really, you are robust to this fast noise. And the main problem here at the moment is then, okay, well, at what resolution is our continuous representation being discretized into this finite set of discrete attractor states? But yeah, I've not yet mentioned the fact that there's fast noise in this system as well, so added non-idealities.
So just as a comment on the interpretation of this, there is some behavioral evidence that things like that might be real. That is, in the nervous system, that there would be a tendency to introduce bias towards implicit categories when you have metric working memory. John Spencer, for instance, done this in color space, where people have to remember a color and keep color in working memory, and then they have a drift towards certain kind of prototype colors that they get that. And the same we did in spatial memory, spatial working memory, and a couple of other instances like that. So to some extent, this might be a problem the nervous system has as well. And it actually builds in biases that might even be meaningful.
Okay. Yes. So here we've taken the view that it isn't useful, and then we're in a sec going to come up with a pseudo strategy to get around it. But if it turns out
you don't get entirely around it, so I mean it's perfectly compatible.
Yes.
It's just you can alleviate.
That's true.
Some of the trade-offs.
Yeah. Okay. Onwards. So I will now, so slightly cheeky way to get around this. So if we very coarsely plot on our energy landscape, very coarsely, I did it this morning, the points at which the points to which our network is being attracted, so the effective, I guess, discrete attractor states that are actually tiling our idealized continuum, then one thing that we could do, because we're using these quantized random Fourier feature S codes, and the fact that we can generate position hypervectors for NEP, is simply say, well, if we want to increase the resolution of our representation, i.e., to have more discrete attractor states which are representing our position, then what we can simply do is to extend our line attractor in the neural space. So if you will stomach the horrible cartoon, now instead of constructing a line attractor by integrating between 0 and 1 meter, say, because we're doing this with VSAs, because we're doing this with VSAs, we could quite easily simply say, well, let's integrate between 0 and 5 meters. Let's form a line attractor which can represent position, a greater range of positions. Then if we very coarsely extend our energy landscape out to 5 meters and assume that our discrete attractor states are occurring with the same frequency as they did in the range from 0 to 1, then this is quite an effective way to increase the number of attractor states along our line attractor, and therefore to realize a higher resolution representation of the position we're trying to represent. But if we return to our original equation for generating the position state story, we'll see that because we're always multiplying our positions p by omega, that increasing our omega from 0 to 1 meter to 0 to 5 meters is just the same as increasing our embedding frequencies by a factor of 5. So equally, we could just relabel what we're looking at here, from 0 to 1 meter again, and simply say, and instead say that we've increased our embedding frequencies omega in order to have a higher resolution continuous attractor network. So let's see if this is actually a reasonable strategy for increasing the resolution of the
Honestly, just doesn't the kernel loop or like it doesn't like so when you have the block code and you spin the blocks, spin the and it usually loops back in on itself. Does it not go
It does
into
not.
Okay, interesting.
Yeah, I have no. It simply does not. Why doesn't it?
I mean, you're doing it differently, but I mean, yeah, I'm just wondering, right? Yeah. Okay, thanks.
Yeah. The reason, so arguably over some domain, it will eventually loop. But for any sizable number of neurons, if you look at, I think the work from maybe feet, what grid cells can vary about the rat's location, the distance over which you'd have to travel in P before you accidentally loop back around on yourself is ginormous. So the kernels don't loop here. The kernels do not loop here, but over some redonkulous range of P, you might accidentally clash again, but it's very unlikely to happen.
Yeah, it can easily happen, right? Just depending on, in your case, the random thing is actually the omega, right?
Yeah.
But depending on what distribution you draw that from, yeah, you could easily make, one that loops, order super high. But yeah, but often with the block code, because it was like a discrete L, the way we were doing the fractional power version of this, it loops on
I see. Yeah.
So, but but yours is, I mean, it's different. So it's because I guess it's the way you choose at the omegas and how that affects the.
Yeah. So if you were to choose the omegas to be integers, possibly,
Right.
then you could end up with a looping round, I imagine. Yes, I think you could force this to loop if you wanted it to, but the fact that your omegas are all different means that you're not going to accidentally clash again, especially for like a large number of neurons.
Right. Very cool. Yeah.
Cool. Thank you for the question. Where were we? Yes. So to quantify the size of our embedding frequencies, because we're making the postulate that greater embedding frequencies equals higher resolution. Again, please keep in your mind that when we're increasing the size of the embedding frequencies, what we're really doing is increasing the length of the line attractor embedding in your neural space. So you're saying, yeah, that you have to be happy with that statement. In going from this is the case we had before where we're going to quantify the size of our embedding frequencies omega by looking at the mean absolute value of omega, which we're calling omega MA here, which for all intents and purposes you can just imagine is the standard deviation of your embedding frequencies omega, if you're more happy with the like the notation in random Fourier features, for example. And here we can see the states that are being represented for the first 32 of like 2,000 neurons. And if we increase our embedding frequencies by a factor of 8, we see that, yes, indeed, the amount of drift in our system, or the amount of error that is incurred as your network state has to self-discretize into one of the available attractor states, into one of the available discrete attractor states, is minimized. And therefore, we're storing much higher resolution representation of the encoding. So whereas over here, if you start your line attractor off at 0.5 meters, say, then after a few seconds, it's collapsed to 0.4 meters. Not very good. Over on this side, we're starting off at 0.5, and then after some time, maybe it's at 0.51 meters or something, which is more acceptable. And then down here, we can see the actual consequence of increasing our embedding frequencies. So it's the fact that our states are, our vector states are varying much more rapidly as you vary your position P. And just to confirm that this isn't a fluke, indeed, as you increase your embedding frequencies, the amount of drift that your network state incurs over a long time period, which is basically representing your discretization error, falls off approximately inversely, which is good news. Now, again, what you should really keep in your heads is that the way that we're realizing this higher resolution continuous attractor is that we're taking our position line 0 to 1 meters and embedding it into a very, very long meandering path in the neural state space, the length of which is determined by our embedding frequencies omega. Now, crucially, this trick is we can only do this trick because we can keep generating new states, which is only possible if we're using these random Fourier feature-esque representations, or more specifically, when we're using neural codes where each neuron is active for multiple positions. So you couldn't do this trick if you're using localist codes, or you can't do this trick with localist codes like those using bump attractor networks, for example. So if you imagine the bump attractor or the ring attractor where you have the neurons that are literally arranged in a ring, then each neuron encodes for one position only, or one small band of positions only. And what this means, at least pictorially, is that your line, your variable from 0 to 1 meters is being represented by a very small loop in, well, not loop. It's being represented by a very small path in your neural space, which you can't increase. So this means that the result of this is that you incur a very harsh trade-off between either trying to put very few discrete attractor states around that, well, along that short path, in which case your representation is stable but has a very low resolution, or you can try some tricks from some other works, which I haven't put here because I ran out of time when practicing this, where you try to increase the resolution by adding many discrete attractor states along your line attractor, and in which case you become arguably higher resolution, but your network is then very unstable due to the fact that, well, yeah, pictorially, if you bombard these systems with noise, this case will be stable. In this case, you will not be stable. However, by the fact that we're using multi-peak distributed codes, you're embedding your continuous variable into a much longer meandering path in the neural state space, along which many more discrete attractor states can live without destabilizing each other, I should say, or yeah, yes, it's simply it's a longer path and therefore can support more discrete states. Yes, that's everything. And we elaborate it more on the paper, which should be coming out very soon. But this basically says that if you're trying to form a high resolution continuous attractor network, then assuming you have non-idealities in your system, using a unimodal code wherein each neuron is active for only one position, such as if you're using a place cell code, is less is less ideal than using something like a grid cell code, wherein each neuron is active for multiple positions, because that will have a much higher resolution. I think someone put their hand up.
Tony.
Yeah.
Yeah, when you have the higher resolution code with the higher frequency, does that affect the radius of attraction to your ring? Like, I'm wondering if there's a trade-off of you can have your more stable states along the ring, but do you lose the ability to attract from further distance away from the ring?
I have no idea. That's a very good thing that is a good thing to look at.
No, I think pictorially it's kind of clear. So on this meandering path, the local minima are as deep as in the low resolution linear path. So that also means that the radius of the basins of attraction are comparable. So you don't lose, you know, your basins of attractions don't shrink. This is what happens when you go to the linear, to the linear path with many local minima. Then you have just these very small basins of attraction.
Okay. The main trade-off though, which I'm not talking about very much, is that as you're making your path longer and longer, effectively you're storing more and more states within your network. If you imagine this from the Hopfield network sort of picture,
right,
whereby
and this is another important constraint, right? This is the memory capacity that needs to be high. So you need to pay attention to memory capacity.
Yep. And again, that's half of our justification for why we're using sparse block codes in the first place. So we don't want to run into issues of memory capacity with our network too early. And so by using these sparse block codes, we in principle should be maximizing the memory capacity of the network. But certainly, if you were to make this too long, so have a windy path around the whole screen, eventually the network will probably break, simply because you're trying to store too many states, and then you have your I've forgotten the phrase, memory breakdown or something. Don't know. But yes. Cool. Also on the subject of basins of attraction, I guess there is, if you have an astronomically ridiculous amount of noise, it is possibly more. It is possible, I guess, in this model that you could make a very large jumps between parts of your line attractor, but you would have to be in a ridiculously noisy situation for that to happen. Cool. So that's told us that we at least in principle can form high resolution we can at least construct continuous attractor networks which represent our variables with a high resolution. I now want to talk about how we make these networks do, I guess, more interesting tricks. So the weights that we've been constructing so far, let's now call them the auto-associative weights. So we've been integrating over our line, just an outer product between terms, very much a la Hopfield, under the hope that with these terms, a certain position state, when projected through this A matrix, this auto-associative matrix, will be most similar to itself again. That's just the attractor dynamics. But we can now consider the effect of adding heteroassociative terms that look like this. So instead of having the X term on the left-hand side, they instead project out the gradient of your attractor states. Now, if you'll just suspend your disbelief for a moment, the effect of these terms is that your states P, so is that your position states will now no longer project exactly to themselves, but will project preferentially to a shifted version of themselves. So if you squint and just imagine that you'll have x of p plus dx of c dx dp, which looks like a Taylor approximation of your shifted states. It looks like a Taylor approximation of your shifted states. So if we constructed a network where your weight matrix consisted just of A plus H, then your network wouldn't be a very good continuous attractor network, because from time step to time step, it would continuously start drifting in the plus C direction. So instead, we want to add switchable dynamics to this, so that you will only get movement in the plus C direction when you're giving the input to make it so. And we do that by binding in the H terms each of these X's to some bipolar dense hypervector, which I'm calling S bar. But for all these equations, you should squint and for the exact details, look at the paper which is coming out shortly. But just to say, this vector S is not a sparse block code. He is dense bipolar. Now, because we're binding each of these X terms to our dense bipolar vector here, this term here is then pseudo-orthogonal to all of our X terms now. So if you imagine X bind S dot X, say, because the S is in there, it will always be approximately 0, at least as far as we're concerned in VSA world. So what we have then is that when you're not giving input to the network, which I'll explain in a second, the H matrix basically doesn't contribute because it's always pseudo-orthogonal to your network, to your position states, and therefore we're back in the regime where your state will project back to itself maximally. However, if we apply inhibition to our network, so this is the same as in the state machines I didn't explain very well earlier. If we apply inhibition to our network such that we are inhibiting or disabling or masking out all neurons for which the S vector is negative, we will leave only the indices where S is positive, and this term here will no longer be pseudo-orthogonal to our state X. And so if you just believe me, if we were in some state X of Q, I've used Q just so we don't confuse Q and P, and we apply a mask on it using the same S vector, which is what I'm using the and symbol for here, then in this case you will project not to the state P, but to P plus C. So this really allows you to have switchable integration dynamics. If you're not giving any input to the network, each state projects to itself. If you're masking out the correct subset of neurons, the state will project to plus C of itself and start moving in that direction. I expect some questions about this point, or not. So here we're looking at the input we're giving to the network, which corresponds to the fraction of the mask that we're applying to the neurons. So here at full input, we're inhibiting a lot of neurons. At no input, we're inhibiting no neurons. And then as we vary, we can inhibit a lesser percentage of the neurons. And looking at the state the network is representing, this is just done by calculating the inner products between every position on the line attractor. We see that our network state is indeed it is indeed integrating our input as we would like, which is good news. Does anybody have any questions at this point? Are we happy?
Oxen unmuted himself. Oxen.
I guess I mean, it seems though you have to have here this giant H matrix.
Yes.
Whereas, like, couldn't you just apply, like an operation that just transforms the state into X plus C, dynamically? That's
so in a way, this is what your H matrix is doing, right? As in your combined.
It's almost like a lookup table, right? It's like every location has a transform. But it feels like
100%.
Right.
So yeah, I mean that's exactly what's going on. An alternative, if you wanted to do this more efficiently, of course, would be to simply read out your network state, convert it to a real number, add plus C, re-encode it, put it back. But my goal here was to really say, well, how can we embed all of this functionality into a continuous attractor network, such that this all of this machinery you're trying to embed is distributed across the entire synaptic matrix. And one question I've had to contend with in my PhD, which I think your question could apply to, your very correct point could apply to all of this. Why should you embed a state machine into 10,000 into a 10,000 by 10,000 matrix when you can describe it in a sentence, for example, or have a very efficient digital implementation that does not require 10,000 by 10,000 synapses. But yes, the H matrix here is just as big as your auto-associative matrix here, and we're just superimposing them to add this integration capability. But then,
Right. Yes, I mean, you need, I guess, like a binding operation for this, though. It's like, is there a binding operation for your way of doing the sparse block code, essentially?
there is there a binding operation for the sparse block code? I think what you said previously explains it in terms of you're effectively making a lookup table such that your Q's project your Q plus C's. So for example, if you were to form your A matrix, so that actually instead of being P here, it was P plus C, then you effectively have a lookup table from P to P plus C. While in this original formulation, you effectively have a lookup table from P to P. So I guess perhaps that explains why there isn't an explicit binding operation here.
Madison, keep going. We've about 8 minutes.
Right, we're going. Generalizing this for 2D is simples. All we have to do is make sparse block codes which represent a 2D vector now rather than just a 1DP. And then a very convenient way to do this is simply to use two of our vectors, use two of our embedding operations and to bind them via LCC binding. Read Dr. Frady's work for more on that. Possibly, Frady. Then where before we were embedding, but where before we integrated just over 1D, now to embed a 2D, now to embed a 2D attractor surface, we simply do a double integral. And also again, where before we were simply, and then we do the same for our heteroassociative terms. However, the difference now is that in the 1D case, we could only choose to project out the derivative dx dp. Since we're in 2D now, we can choose to project out any linear combination of dx dp1, dx dp2, and so by choosing your A and B coefficients, you can decide at which point the network should move or integrate, basically completely freely. And we can program effectively onto our plane which direction it should move. And this is just writing the exact same thing, but in a more compact fashion. So the fact, and then adding the switchability in again by binding it to our S vector. And yes, so at every point we can impose a vector field onto our manifold effectively, which we activate with the correct input. Yes, so here we see that working. Unfortunately, no cool animations yet. So here are the three vector fields which we've imposed upon our manifold. Again, as Mr. Frady correctly pointed out, we're effectively saying we're effectively programming onto our 2D sheet at every point that the direction in which the network should move in response to input. And we see that the network indeed does the correct, well, it does the correct movement for the inputs we give it. So we've put one vector field on for clockwise rotations, and then two for the orthogonal directions, and we see, yep, the network does do that. Very good. Now, generalizing this to arbitrary manifolds is not difficult. It just writing down the maths is a bit horrible. But basically, to embed a plane, we integrated over a plane. To embed something sillier like a sphere, for example, you simply integrate over a sphere of states and embed all of those states into your attractor network. And then, of course, you have a lot of freedom in what vector fields you put onto your network. So the direction that your network should move in response to input. Here, I've just chosen to have 3 vector fields corresponding to rotations around each of the axes, which could plausibly be used to integrate 3D rotations, for example. Or you can embed even sillier things like a Mobius strip or a Klein bottle, whatever your heart wishes, basically. So that's quite cool. And it should be noted, if you look through the literature, even the recent literature on continuous attractor networks, there doesn't really exist a method for going beyond embedding linear subspaces into continuous attractor networks and embedding them into, and embedding entirely arbitrary manifolds with entirely arbitrary vector fields on them is kind of new, which is good. Yes, so there's a better figure. In digital, my overall motivation for this is that in building up digital computers, we've created hierarchies of increasing abstraction, whereas for neuromorphic computing and arguably more generally artificial networks, we don't really have a way of going from your low-level neural description up to your high-level function. However, obviously the way we currently achieve this in the era of deep learning is simply by throwing everything into a black box and shaking it till it works. But hopefully you're somewhat convinced that on the journey to achieving more high-level function, that you can begin to build up, you can begin to create a hierarchy of abstractions which could exist in neuromorphic computing and arguably biology. So having a attractor network sitting on top of your analog spiking neurons, for example, and then really using the structure of VSAs to embed symbolic computation into those. And if someone takes this work further, hopefully that will eventually get closer to achieving some high-level function. That is everything. There's absolutely thank you very much for your attention. I've almost ran out of time. Yes. Does anybody have any questions, please?
Thank you, Madison. So we have time for maybe a quick question. So we had a great discussion. Bruno, please.
Oh, yeah. Madison, that was fantastic. I had a question about if you can go back to the slide with the A plus H dynamics and the S vector that you bind. It's interesting. So this is, roughly analogous to like in Ketchen-Zhang's circuit. He has the symmetric term and an asymmetric term, and then he gates in the asymmetric term with a single scalar variable gamma.
Yes.
And so I was just wondering, like, why did you choose to do it? It seems like you could have done a similar thing here. Why did you choose to do with this S vector? I think in the time sense, I think I came up with an answer, which is that it appears like in his system that gating has to be sort of on the dendrites, where like in your system here, you can do it element wise. Is that correct? Or how do you think about that?
Yes, and entirely. So I was working under the constraint that you're not allowed to simply alter your weights during operation. If you were allowed to literally modulate your weights, then a much easier way of doing this would simply to have, say, a P plus vector field term inside of here, which is modulated. So I'm coming out. So the reason I did it in this way is really coming from the perspective you're not allowed to modulate your weights. I can't speak about biology, but at least in neuromorphic computing, if you want to be able to modulate all of your weights over a range of values, you would possibly get laughed out of the room by a circuit designer.
All right.
So and in any case, I would argue that this is a simpler I think if a simpler mechanism exists, then it should be explored. As in, this is adding some complexity to our eyes at this point in terms of how the matrix is constructed. But then the method of triggering an integration, yet, as you say, is as simple as element-wise disabling certain neurons, which is, I think, is cheaper than the mechanisms in terms of hardware requirements that the Zen model would need.
I see. Thanks.
All right, I think it's time to thank Madison for the great talk, and thank
Thank
you,
you. Thank you very much, all.
contributed to discussions. Really great. So I see you in a couple of weeks, or maybe in, well, slightly more. Please check the schedule, and I will send the calendar invite. So see you next time, and goodbye for now.
Thank you.
Thank you. Bye.